Hello students and welcome. Today we're going to dive into the truly fascinating and highly logical world of trigonometry. In this explainer, we'll methodically build up your understanding of ratios, unearth some beautiful mathematical identities, and most importantly, learn how to apply them with absolute confidence.
Created by MindSticks Foundation Trust. All right, let's look at today's roadmap. We are going to quickly recall basic trigonometry, introduce reciprocal ratios, check out standard angle values, prove the fundamental trigonometric identities, and finally, solve some real mathematical examples together.
Section 1. Recalling basic trigonometry. Let's just take a quick moment to refresh what we all studied back in Standard 9 regarding acute angles in a right-angled triangle. Okay, remember the core definitions. For any acute angle, let's call it theta, the sine ratio is simply the opposite side divided by the hypotenuse. The cosine ratio, that's the adjacent side over the hypotenuse, and the tangent ratio is the opposite side divided by the adjacent side. Keeping this right-angled triangle clearly in your mind is going to be absolutely essential for everything else we do today.
Section 2. The reciprocal ratios. Now, we're going to expand our vocabulary a bit and study some new ratios. But don't worry, these are literally just the multiplicative inverses, or the flipped versions, of the basic ones we just recalled.
So, the very first new ratio we're introducing is the cosecant ratio, which we write briefly as cosec. By definition, cosec theta is exactly 1 divided by the sine ratio. Therefore, if sine is opposite upon hypotenuse, cosec simply flips that fraction right over. It becomes the hypotenuse divided by the opposite side. Simple, right? Following that exact same logic, secant, or sec theta, is the multiplicative inverse of the cosine ratio. And finally, cotangent, written as cot theta, is the multiplicative inverse of the tangent ratio. A very good trick to remember is this. Sine pairs with cosec, cosine pairs with sec, and tangent pairs with cot. You'll master these pairs in no time. Let's actually see how this works algebraically on a triangle. Notice how cosec theta becomes the hypotenuse AC over the opposite side AB. It perfectly inverts the sine ratio, which was AB upon AC. This reciprocal relationship, students, forms the absolute bedrock of all the proofs we're going to tackle.
Moving on to Section 3, Standard Angle Values. With our 6 ratios now clearly defined, let's look at their specific numerical values for our standard acute angles.
This reference table is so crucial, but notice how beautifully the reciprocal logic applies here too. It's like a giant puzzle where everything fits. For instance, look at the 30-degree column. Because we know sine 30 is 1/2, we can simply invert that fraction to find cosec 30, which gives us exactly 2. Literally, memorizing the top 3 rows gives you the bottom 3 rows for free.
Section 4. Fundamental Trigonometric Identities. Pay close attention here because we have reached the most important part of today's class. We will now systematically derive the 3 fundamental rules that govern this entire chapter. Let's prove the very first identity step by step. If we take our right-angled triangle and apply the good old Pythagoras theorem, we get base squared plus height squared equals hypotenuse squared. Now here is the clever mathematical trick. What if we divide the entire equation by the hypotenuse squared? When we do that and substitute our trig ratios back in, magic! We brilliantly prove our first fundamental identity. Sine squared theta plus cosine squared theta equals exactly 1.
But we don't stop there. We can take that very first identity and divide it entirely by sine squared theta. Doing that gives us our second identity. 1 plus cotangent squared theta equals cosecant squared theta. Similarly, dividing that first identity by cosine squared theta gives us our third identity. 1 plus tangent squared theta equals secant squared theta. Keep these 3 equations in your mind. They are going to be your absolute best friends in trigonometry.
Section 5. Solving mathematical examples. After all, theory is only as good as its practical application, right? Let's see how establishing these fundamental rules builds our ability to actually solve complex problems.
All right, here is our first practice problem. If we are given the specific value of sine theta as 20 upon 29, how can we mathematically deduce the exact value of cosine theta? To make sure you have a really deep understanding, I'm going to show you 2 completely valid methods to solve this. Method 1 utilizes that newly proven algebraic identity we just talked about, substituting the value directly. Method 2, on the other hand, relies purely on geometry. We construct a right-angled triangle,
assume the sides are in the proportion of 20k and 29k, and just apply the Pythagoras theorem to find that missing adjacent side.
And this right here illustrates the sheer beauty of mathematics. Whether you square the fractions and use the algebraic identity in Method 1, or you calculate the side lengths physically in Method 2, both paths lead to the exact same destination. Cosine theta equals 21 upon 29. It proves that our mathematical rules are perfectly 100% consistent.
Let's level up a bit. Look at example 3. It's a bit more challenging. It gives us an equation. 5 sine theta minus 12 cosine theta equals 0. Now don't panic. Here, we just must perform a simple algebraic rearrangement first. By moving terms around and dividing, we quickly find that tangent theta equals 12 upon 5. Only then do we bring in our 1 plus tan squared identity to effortlessly find secant theta. From there, finding cosine, sine, and finally cosec theta is a breeze. You see, step-by-step logic always wins.
Now, in your examinations, you will frequently encounter these classic show-that proof problems. For a problem like example 5, our explicit goal is to methodically convert the complex terms on the left, secant and tangent, into basic sine and cosine ratios. The trick here is to rationalize the denominator inside the square root by multiplying by 1 plus sine x. This creates a perfect square in the numerator and triggers our fundamental identity in the denominator, beautifully proving that the two sides are perfectly equal.
Finally, example 6 introduces a very important, slightly advanced concept, eliminating theta entirely. We are given x and y in terms of cot and cosec. By smartly adding the equations together to isolate cot theta, and then subtracting them to isolate cosec theta, we can utilize our second fundamental identity. Cosecant squared minus cotangent squared equals 1. By substituting our x and y expressions into this identity, poof, theta vanishes completely, leaving us with a very neat algebraic equation purely in terms of x, y, a, and b.
So, the absolute most crucial takeaway today, students, is understanding, deriving, and truly memorizing those three fundamental identities. They are the master keys that unlock every single problem we discussed today. Having seen these structured examples, I strongly encourage you to apply this logic confidently to practice set 6.1. Are you feeling fully prepared to tackle them on your own now? I certainly believe you are. Keep practicing, keep reasoning step by step, and your mathematics will remain incredibly strong. Thank you for learning with us today.